All right. Today we are going to move forward and we are going to start talking about electricity. And this may seem like a rapid change of topic, but really it's not. We will talk about electricity, we'll talk about electric fields, we'll talk about circuits, we'll talk about magnets and magnetic fields, and then we'll come full circle and we'll be back talking about waves again when we talk about light. So, in this module, you're going to be learning about electric charge and how charges relate to each other. And the father of our discussion was Ben Franklin, who lived from 1706 to 1790. You guys probably are familiar with Ben Franklin from history class. There's all sorts of stories about him, including the famous one about him flying a kite to examine lightning strikes. So what did he find out? What he found out was that there are two charges in nature, positive and negative. And he did not know that they were electrons and protons because this was way before we understood the nature of the atom. He described electricity as a fluid because when he looked at lightning bolts, lightning strikes, it looked as if electricity was a fluid flowing through the sky. And either that electricity was present and was positive or it was absent, negative. But he was able to show that objects that have opposite charges attract and that objects that have like charges repel, and that charge is quantized, that it is made up of discrete units. So there's some fundamental unit or value of charge, and when you gain a charge, you gain multiples of that. And we now know that's electrons, right? The electron has a certain charge on it. And if an object has a total negative charge of, 2 coulombs, we can actually determine how many electrons are in, producing that negative 2 coulomb charge. And also he was able to verify that charge is conserved. It doesn't just appear out of nowhere. When we build up a static charge, if something becomes, gains a negative charge, the other thing has an equal positive charge. So you don't just gain charge. It doesn't disappear. It doesn't just, appear out of nowhere. It comes from somewhere else. That base unit of charge is the charge of an electron, which is negative 1.6 e to the negative 19 coulombs. So coulomb is the unit of charge that we use. And protons have the exact same charge, but they're the opposite polarity. So they have a positive 1.6 e to the negative 19 coulombs of charge. So for example, if we have something that has a total of 1 coulomb of negative charge, we can figure out how many electrons are in that, because we can take that total charge of negative 1 coulomb, and we can divide it by the charge of 1 electron. So 1 divided by 1 exponent, negative 19. And that would be 1 times 10 to the 19 electrons. So my symbol for electrons is an E with a minus over it. So there's 1 point E to the 19th electrons on the surface of that metal surface that is together has a total charge of negative 1 coulomb. So one thing that you're probably very familiar with is static electricity. Static electricity, obviously, you can get shocked, right? You can be walking down a hallway with carpet, and when you go to reach to open the door, you might feel a shock. So exactly what is causing that? Well, static electricity can form in a couple of different ways. One way is by friction. So let's say that you comb your hair, and when you're done, you notice that your hair is standing up. And what's happened is that originally the surface charge was evenly balanced on the comb. So for every positive charge, there was a a negative charge. And same thing on your hair. But when you started rubbing your hair, the comb is made out of rubber, the hair is made out of hair, and those substances have a certain electron affinity. They have a tendency to keep the electrons in their outer shells very tightly, that they hold on to them. So if it has a high electron affinity, it tends to hold on to those electrons in the outer shell. If it has a low affinity, it can't. The force is too weak to hold them. So when you rub these two surfaces together, the one with a high electron affinity is going to gain electrons, and the one with a low electron affinity is going to lose electrons. And when you lose electrons on the hair, it becomes more positively charged, and you gain electrons on the comb, it becomes more negatively charged. And using our rules about charges that Ben Franklin found, that if your hair has an overall positive charge, then those hairs, which are all positively charged, will repel each other. So it'll look like it's standing up because they're repelling each other. But at the same time, they're attracted to the negative charge on the comb. So if the comb were to gain -1 coulomb of charge, the hair would become +1 coulomb, would have +1 coulomb of charge on it. So that's that conservation law that we're talking about. The other way that you can charge something is by contact, right? By literally charging something up, giving it a negative charge, and then touching a conductive material. Those electrons will flow onto that conductive material because it's more positively charged. And now that material becomes negatively charged. So it has a net negative charge, and the object that originally had the charge is now more positive. So this gains 2 coulombs. This gains a negative charge of 2 coulombs, then this will have lost that much and will now be more positive by that much. And in fact, you don't even have to touch. You can just bring it near, right? So if I take this rod that has a negative charge on it and I bring it near without touching, those electrons, so what we want to assume is that the sphere to begin with has an even distribution of positive and negative on its surface. So the negative field around this is going to repulse the negatives on the surface of the sphere and push them away. So one side of it will become, on the other side will become negative, but that also makes this more positively charged. So I've induced a positive charge on the surface without even touching it. So that means that obviously if you can induce charge and charges attract and repel, that there's a force acting on those charges, and that force is called the Coulombs force. We're going to call it Fe as our symbol. And it turns out that when you have two charges that are separated by a distance r, the symbol for charge is Q, so we're going to call this Q1 and Q2, and the distance between them is r. It turns out that the bigger the charges are, the more force of attraction or repulsion they'll have, and the further apart they are, the less. It turns out that force is inversely proportional to the distance, but it's directly proportional to the charge. So this is kind of similar to gravitational force, right? When we learned about gravitational force between two masses, we learned that there was a constant called big G, and that it was directly related to M1 and M2, and it was inversely related to r squared. And if we made a graph of that with gravitational force and r, it would look something like this, right? And this G was a constant. Difference is that gravitational force is always attractive. It's never repulsive, but it does have the same kind of mathematical relationship between the things that cause it and the distance between them. So electric force is another constant, it's K, the Coulombs constant, times the two charges in coulombs each, divided by r squared, where Q is charge in coulombs and K is a constant, which we'll talk about in just a minute. So that constant is 8.99 times 10 to the 9 newtons per meter squared. And if we compare these two laws, the formulas look really, really similar, right? They look super similar. They're both directly proportional to what causes them. They're both indirectly proportional to distance squared, which means if I double the distance, then the force will be 1/4, right? It'll be 1/4 of what it started at. If I triple the distance, the force will be 1/9 as much, right? That's the inverse square relationship. But electric force can be attractive or repulsive, and electric force is stronger. So these are the differences between them. If we make a plot of Coulomb's force, where we put force on the y-axis and r on the x-axis, then we get an inverse relationship. And the generic formula for inverse relationship is a all over x squared plus b, where b is the intercept. So let's just assume that we're not going to worry about that right now. We're just going to look at that a. So if we relate this to the Coulombs equation, Fe equals k q1 q2 all over x squared, it looks like this number here is what that coefficient a is. So a is equal to the Coulomb's constant times the value of the first charge times the value of the second charge. So in this case, we have a Coulomb's constant. It looks like it's 1.47 e to the 9. I can't read it very well, but let's say it is. If we know what Q1 and Q2 are, we can solve for K. Also, if we want to verify that this is indeed an inverse square relationship, we can, instead of plotting F versus R, if we plot FE versus R squared, 1 over R squared, right? Then, and we kind of rearrange it so you can see that, it would be equal to K Q1 Q2 times 1 over R squared. So if we plot this on the y-axis and this on the x-axis, we should get a line. We should get a line. So Fe equals K Q1 Q2 times 1 over R squared. This is y equals mx, right? So this is on the x-axis, this is on the y-axis, and the slope would be equal to whatever the coefficient is, that unit, times whatever the charges are that you're looking at. So let's just do an example. So we've got 2 electrons, so I'm going to put 2 electrons here. Remember that the Q of an electron is negative 1.6 e to the negative 19 coulombs. And let's say that they're 2 centimeters apart. So one thing we want to do is we want to make sure that this is in meters. So this will be 0.02 meters. Okay. If we want to draw a force diagram, these are going to repulse each other. So they're going to repulse each other equal and opposite. When we use the Fe equation, we will be finding the value of that force, how big that arrow is. And we also know that K is 8.99 e to the 9 newtons meters squared all over coulomb squared. So if we want to find the value of E, Fe is going to be equal to K Q of the electron times Q of the electron all over R squared, which is 8.99 e to the 9 newtons meters squared all over coulomb squared, times negative 1.6 e to the negative 19 coulombs. And I'm going to square that because they're both the same. divided by the value 0.0200 meters squared. I'll put that in our calculator. And here's where you're really going to need to be able to use your exponent button. So if you don't have an EXP button, you want to use the EE button, not the E to the X or anything like that. You want to use the EXP button or the EE button on your calculator. So 8.99 exponent 9 times the quantity 1.6 exponent negative 19. And you may say, why didn't you put a negative in there, Miss Knight? Well, I should have. So let's redo that. 8.99 exponent 9 times the quantity negative 1.6 exponent negative 19, and we're going to square that. Actually, I need to go back one place. All right, let's start over. 8.99 exponent 9 times 1.6 negative exponent negative 19 times 1.6 negative exponent negative 19 equals divided by the quantity 0.02 times 0.02. It's a very small number. I'm going to put it in exponential notation. So I should be getting, and I missed it, 5.75 e to the negative 25 newtons. Notice that the coulombs go away and the meters go away. I'm left with newtons. So these arrows represent that size. Okay, so now, remember these are forces. So let's look at a little more. We've got a 4 microcoulomb charge and it's placed 2 centimeters from a negative 2 microcoulomb charge, which is 4 centimeters from another negative. So we're just going to make a like this. So we're going to have 4 microcoulomb and it's going to be placed 2 centimeters from a negative 2 microcoulomb, which is 4 centimeters from another negative 2 microcoulomb. We want to know the net force on this. Well, on the 4 microcoulomb. So let's just draw a diagram here. So this is, we're going to call this Q1 and call this one, actually this one's going to be Q1, this one's going to be Q2, and this one's going to be Q3. All right, so the first vector we're going to show is that Q2 is going to be attracted to Q1, right? Because they're opposite. So Q1 is going to feel this force. So this will be the force due to Q1. And it's also going to be feeling this force of attraction to Q2, right? So if I were to think about this, if I find this force and this force, they're both in the X direction or the I direction. So first thing I'm going to do is I'm going to find the length of both of these. Okay, I'm going to find and actually this should be Q2 and this should be Q3. I'm sorry. This is the force due to Q2. This is the force due to Q3. So the first one I'm going to find is that force due to Q2. It's going to be Q1 times Q2 all over the distance between them squared. And I'm doing the absolute value because I really don't care about positives and negatives right now. It's going to be 8.99 e to the 9 newtons meters squared all over coulombs times 4 e to the negative 6th and negative 2e to the negative 6. Now, remember that micro is 10 to the negative 6. So we're going to make sure that everything is in coulombs and meters. And this is going to be 0.02 meters squared. These are both in coulombs. So notice my coulombs are going to go away. My meters are going to go away. I'm going to put this into my calculator. And I just want the absolute value of it, so I'm going to drop that negative. So I have 8.99 exponent 9 times 4 exponent negative 6 times 2 exponent negative 6 equals divided by 0.02 squared, which is 1.79 e to the 2, or 179 newtons. Okay, FQ3 is going to be 8.99 e to the 9 newtons meter squared all over coulomb squared times 4e to the negative 6 coulombs times negative 2e to the negative 6 coulombs all over the total distance. Well, the total distance is 0.02 plus 0.04, or 0.06 meters squared. I'm going to put this in the thing. 8.99 exponent 9 times 4 exponent negative 6 times 2 exponent negative 6. Once again, I'm just finding the absolute value of these things. And then I'm going to divide them by the quantity 0.06 squared in quantity. And that's going to give me 1997, or 2.0 e to the 1. So that's going to be 20.0 newtons. Now, what I want to know is the net force, right? So if I were to write these out, FQ2 is 179 newtons in the I direction, positive I direction, and FQ3 is 90 newtons in the I direction. So F net is FQ2 plus FQ1, which is 179 plus 90, which is 269 newtons in the I direction, in the positive I direction, or due east.